getting set up, let me introduce her. So Bettina is a professor of theoretical chemistry at the Freie Universität of Berlin. She completed her PhD at ETH Zurich and was actually a postdoc with Frank Noe, who was one of the speakers earlier in the session. Bettina's interests lie in molecular dynamics simulations, QM/MM methods, reaction networks, enhanced sampling, dynamical reweighting, and she's interested in applications to proteins, peptides, riboswitches, and enzymes. And so Bettina has won a large number of awards. So let me just mention a couple of them. So in 2016, she was elected membership to the Jung Academy of the Berlin Brandenburg Academy of Sciences and Humanities, and also a member of the German National Academy of Sciences, Leopoldina. And in 2018, she won the Hans G.A. Hellman Prize for Theoretical Chemistry. So we're very pleased that Bettina can join us today. And please, Bettina.
Thank you very much for this kind introduction. Thank you for including me in this session or in this conference at all, and for putting this together across 3 different time zones. I really enjoyed the afternoon, at least the afternoon in Europe, and I don't know what time zones you are in. And what I brought you today is something a bit about dynamical reweighting and path probability ratios to sample rare events. So rare events. Well, yeah. That hardly needs an introduction, right? So if you think of molecular dynamics, these molecular dynamics occur across relatively narrow transition paths. We can think of this like mountain paths across, mountainous energy landscape. And even though these paths are narrow, right? So they don't cover the entire space. We still have huge barriers along these paths, and we can speed up the simulations, of course, by biasing these potential energy function, and for example, using something like metadynamics, and then we explore the state space faster. But the drawback is, of course, because we speed up the rates, the dynamics get distorted. And there are lots of methods that recover the stationary properties, but we would also be interested in recovering the dynamic properties. And methods that try to do that are called dynamic reweighting. And there has been quite some effort in developing dynamic reweighting methods. So there are different ideas. We tried to classify some of them, actually so many that we couldn't classify all of them in this short review over here. So one idea would be to rescale the transition flux across a state in the conformational space. So to have if you start here in this cell and then you transition out into the neighboring cell, the transition probability will be different depending on whether you simulate at a blue potential or at a green potential. So blue is going to be the simulation potential, and green is going to be the target potential throughout the talk. And then there are other methods that try to reweight the overall transition probability from one state I to another state J. Reweight a Markov model, essentially, often based on likelihood functions. Trum and Dum are examples. And we've been focusing on methods that kind of reduce this or decompose this overall transition into individual paths that make their way from I to J. So instead of reweighting the entire transition, we reweight individual paths, and that's called path reweighting or Gilsanov reweighting. And as I just said, I want to focus on path reweighting today. And one reason for this is that this is actually, or in principle, an exact method. So you don't make any assumption in the reweighting process, in principle. And what I will talk about today is this in principle. You see, the problem is that, and that is not only in path reweighting, that applies to many analysis techniques that we have, is we tend to simulate Langevin dynamics. So we use a Langevin thermostat that has a friction term and a random force to represent a thermal bath. But what we analyze is often based on overdamped Langevin dynamics. And a lot of theory has been developed for overdamped Langevin dynamics and not so much for Langevin dynamics. And in particular for path reweighting, we have a lot of equations or a lot of theory for overdamped and for underdamped Langevin dynamics. This is lacking. This is because overdamped Langevin dynamics is a first order stochastic differential equation, right? So you have a first order derivative over here, first one derivative with respect to time, whereas this is a second order stochastic differential equation where you have a second order derivative with respect to time, so an acceleration, and that seems to make things very, very complicated for the mathematicians. I don't know. So we're going to look at this discrepancy between overdamped dynamics and underdamped Langevin dynamics. But let me introduce path reweighting first. So what we would be interested in is reweighting a dynamical property, and often this is some sort of a correlation function. And as an example, I pick here the transition probability, or the overall probability of observing a transition from I to J. And you can formulate this transition probability, Cij, as a path integral, where you integrate over paths of length tau, so of a certain length. All the paths have the same length, and you evaluate the initial point and the final point with a indicator function. So if the path starts in I and ends in J, then this makes a contribution to the path integral. If you then discretize this for discrete paths, this looks like this. Here, the blue is your simulation, right? It's what you simulated, little snippets of your simulations of length tau. That have an initial point, and then after n time step have a final point. And you can really imagine that you have a long simulation that you snip down into little pieces. And if they start in I and if they end in I, then this evaluates to 1. So this little path makes a contribution of 1 to the overall count of transitions that you've seen in your simulation. And then you divide by the number of paths that you have in your simulation. And blue means that the path has been generated at the simulation potential. And here in our case, this is usually a normal potential, v tilde plus some bias u of x. Now path reweighting. So this is what you would normally do if you simulate, and then you count the number of transitions and you get a rate or a transition probability. Now in path reweighting, you would like to do that. You would like to estimate the rates of your target potential by analyzing simulations conducted at the biased simulation potential. You would like to have the rates of the green potential by looking at trajectories sampled at the blue potential. And of course, the equations in principle look the same as previously, only that you now have to introduce a different probability density over here. So here we had the path probability for the simulation potential, and now we have the path probability for the target potential. And formally, we can rewrite this, or we can decompose this into a product of the original, the blue path probability, times a reweighting factor. And if we discretize this, what happens is that every path sniplet from x0 to xn that starts in I and ends up in j makes a contribution to the path integral, but now not with 1, but only with this relative probability here in red. So in order to estimate the correlation function at the target potential, we need to sum over all paths in our simulation, check whether they start in I and end in j, and then we need to calculate this relative weight. And we decompose the weight into 2 terms. One is the probability of finding the system in the initial state, and the other is the probability, the actual path probability of seeing the path given that the state has started in x0. So the probability of the path omega given that we started in x0. And these are just ratios of the relative path probabilities in the target potential and the simulation potential. So our goal now is to calculate these factors. And the G factor is actually simple. The G factor is just the Boltzmann factor of the bias. If you divide the Boltzmann probability densities, you end up with this Boltzmann factor, which contains the bias over here. And next we need to calculate, or we need to come up with a model for the path probability ratio. So we need to calculate the probability of observing a little path given that the path has started in X0. And this is done by decomposing the path into the individual integration time steps. So if you have n integration time steps, then each of these dots is the progress in your simulation at each at every integration time step. And then the overall path probability is the probability of observing these individual steps. So the overall path probability is just the product of observing these individual steps. And so there's no there's no Markov assumption from going here to here. We only have the Markov assumption at the integrator level, and this is Markovian by construction. The problem is that now the single step transition probability, this one over here, going from xk minus 1 to xk, that of course depends on the integration scheme. So here we need to insert knowledge about the integration scheme, and that's where the difference between overdamped and underdamped Langevin dynamics comes in. For overdamped Langevin dynamics, these equations are well known, and you don't need to go through them. I'm just saying the slide is supposed to tell you that we all know them, right? So that they have been well documented. So this is the typical integration scheme for an overdamped Langevin dynamics. That's Euler-Maruyama, and we have the single step probability that looks like this. And if we take the ratio of single step probabilities with target potential and simulation potential, we end up with a probability ratio M that contains here the difference of the gradients and the difference of the gradient squared. So this is well known. And if you simulate at overdamped dynamics, this really works like a charm. So what we did here is we simulated at this double well potential, and we reweighted to the triple well potential. And the simulation was conducted with overdamped Langevin dynamics. And you see, we are not terribly squeamish with distorting our potential. And we make it smaller and we make it tighter, and we introduce additional barriers where there used to be additional barriers and minima where there used to be maxima. So you can actually do quite a bit with the potential without breaking the method. And what we use to benchmark the system is the Markov state model eigenvectors. So this is the first one is the Boltzmann distribution, and the second one represents the exchange between this minimum and this minimum over here across the central minimum, and the second one represents the exchange between the central minimum and the ones on the side. And then we have timescales associated to this. So that's 2000 time steps and 600 time steps. And black is the reference simulation where we actually simulated in the black potential, in the triple well potential, and red is the reweighted trajectory. So we simulated in a double well potential and reweighted to the triple well potential. And for overdamped, so if you conduct our simulations with overdamped dynamics and we reweight with overdamped dynamics, this is right spot on. Now but if you want to simulate a molecule, you of course turn on Langevin dynamics, underdamped Langevin dynamics. And one idea would be, well, if we have all these equations, we just use them, right? We ignore the problem and we use it. But this unfortunately fails very badly. So we simulated at the double well potential using underdamped dynamics and reweighted to the triple well potential using the known equations. And what happens is that not even the eigenvectors are recovered. So even the Boltzmann distribution is badly distorted. So you get very wrong results if you just use these overdamped Langevin equations, overdamped Langevin reweighting factors. And what we had to do now is to develop a reweighting factor for underdamped dynamics. Okay, and that's in this paper. So we used a very simple Langevin integrator to wrap our heads around this, to understand how the method works. So that we call it ISP scheme, and it's actually an integrator that we simplified, right? So it's not an actual integrator, right? So you won't find that in an MD program. It's a very simplified thing. But it is the advantage of this is that you can actually kind of see the basic things that's happening. And the basic idea here is that an integrator is actually a transformation from a random number to a position. So here's the update in the position space, and it takes the initial position and it takes the potential. And most importantly, it takes the random number. So this is a very complicated function that transforms a random number into a position. So you can think of an MD integrator, and that is true for all Langevin integrators, for all stochastic integrators. You can think of them as a transformation from random numbers to positions, and vice versa. So because also you can also invert this transformation. So there's a direct mapping between random numbers and positions. And the upshot of this is that you can replace your path probability by the probability to draw this string of random numbers. And the probability to draw this string of random numbers is of course known, because we know that this is, we construct them to be standard Gaussian random numbers drawn from a standard normal distribution with a probability like this. So given the random numbers, we can very easily calculate the path probability like this. Okay, so here's the idea. So the same thing in pictures, so to say, right? So in an MD simulation, what you do is you generate a sequence of random numbers. You have an initial point, you have your integrator equations, and that's kind of a black box, and it returns positions. And now if you want to calculate the path probability, you reverse this process. You take your positions and you reverse the equations, and you get out the sequence of random numbers that you would have needed to generate this path, and you can calculate very easily the random number probability, which is then equal to the path probability. And you would do the same thing for a different potential. So you would take the path that you have generated, and then now you would like to invert the integrator equation for a different potential. You get out a different sequence random numbers, and then this is the probability of drawing these random number sequence for the target potentials. And then by comparing these two probabilities, you can get to a relative path probability. So we can look at this like this as well. So here's the path that you have generated, and you would like to reweight this. You have generated this as at the simulation potential, and would like to reweight this to the target potential. Here in solid, we have the random numbers that are needed to generate the path at the simulation potential. Then here, the dotted lines are the random numbers that are needed to generate the path at the target potential. And if you reweight, or if you take the ratio of these two probabilities, you can get the path probability ratio M that you would need to reweight your transition counts. Now, the nice thing is now that we can formulate the random numbers at the target potential as well, the original random numbers eta k plus a little delta, plus a little shift here. So we can get to the dotted line by taking the solid blue line and adding this little shift to the target random numbers. And if we do that, if we construct or we write down our tilde eta k like this and insert this into this equation, we end up with a formula for the path probability ratio that looks like this, because that's a binomial formula over here. So here we have a binomial formula, and then the first term cancels, and you're left with these two terms. So why is this useful? This is useful because this is the random number for the simulation at the simulation potential, and that is something that you don't have to calculate. That is something that you can just record during your simulation, and the only thing that you need to calculate is this little orange shift. So the idea now is that in order to calculate this path probability ratio, you record the random numbers of your biased simulation eta k. you calculate delta eta k, and you evaluate this function. And for the ISP scheme, delta eta k looks like this. We have here the gradient of the bias, and we have here a factor xi delta t, that's the friction times the time step. And we have here a prefactor that depends on the temperature. So this is exact, and it's much easier and less error prone to implement than calculating the full path probability in terms of positions. We also derive the full path probability, but this is really a much cleaner and simpler formulation. So with this, we can now do exact reweighting for this ISP scheme. But the story goes a bit further, because if you look at this and compared, so this is the expression for delta eta k for the Langevin integration scheme, and that's the one for the Euler-Majorana scheme. And what immediately comes to mind is that they look very, very similar. So we have the gradient of the bias over here. We have this prefactor that contains the temperature and the mass. And then we have here a factor that essentially evaluates to 1, because xi delta t is very small for MD simulations. And we have analytical proof that these two factors, they're really, really similar up to 4th order, right? So up to 4th order, you can replace this factor by this factor. So what you could also do is you could record your random numbers at your simulation potential during the simulation. And then the correction for the reweighting, you can just replace by this Euler-Majorana scheme at delta eta k. So here's the error analysis between the exact expression and the approximated expression. So the difference between ISP and Euler-Majorana, difference between underdamped and overdamped dynamics. And as a function of the time step, essentially, MD simulations are conducted here in this regime, and you see they're right on top of each other. And this is the absolute error in delta eta k, and that's the relative error. It's really 0. But what is important to point out is that so if you have an update in the position from xk to xk plus 1, this is composed of a deterministic update like this, and then a random update like this. And that is very different for the different dynamics. So this, if green is Langevin dynamics and blue is overdamped Langevin dynamics, this might very well look like this. We have very different, the overall progress is composed of very different sub progresses. But what is similar is the sensitivity of the random number on the change of the potential. So this delta eta k is the same for underdamped and overdamped Langevin dynamics. So the delta eta k represents how much does the random number change when I change the potential. And that seems to be the same for both dynamics. Okay, so let's try this. So that's our model potential. We simulate at the double well potential using Langevin dynamics. Black is the solution the reference solution when we actually simulate at the target potential. And in green, we have the reweighted results from the double well to the triple well potential. So that works well. And in orange, we have the reweighting where we've replaced the delta eta by the Euler-Majorana expression, and that also works very well. So that's right on top of each other. So obviously this approximation works very well for the ISP scheme. And for the implied timescales over here, actually the approximation seems to work even a bit better than the analytical result. And the reason we think is in numerics, because we have to calculate less exponentials here in this reweighting factor than in the approximation. So the approximation has to calculate less exponentials than the actual analytical exact expression. So we think that this might be the reason why the implied timescale of the approximation are actually a bit better. So now we have what we have achieved now is a method to reweight Langevin dynamics, and that in fact works also for molecules. So what I show you here is a beta hairpin peptide. That if you simulate this in an unbiased simulation, we have here 17 microseconds. The only thing that you see is a slight opening and closing of the ends. And these are the two states that you would see in an unbiased simulation, open and closed. And they do that on a time scale of a nanosecond. And but we know from experiment, well, it's been designed like this, that this is a molecule that open and closes. It's a molecule that has been designed to open, unfold, and refold. So we biased along these three of these hydrogen bonds, so three one-dimensional biases, and in fact saw full opening and closing of this peptide. And then we reweighted this and obtained a reweighted Markov model that has three states, A, B, and C, where B is the fully closed, and we have transitions to half open states, left and right. And a state that was sampled, a fully extended open state that was sampled, got reweighted to very low populations over there. So this works. And we have 1.4 microseconds of simulations to conduct this. So an order of magnitude of simulations less than previously. And if I'm not quite sure how I'm doing time-wise, I have a little.
Yeah, you have about 5 minutes left. We started a little late.
Oh, excellent, excellent. So what I've shown you here is now something that works for a very specialized integrator, right? So for this ISP integrator that we constructed, because that was what we could handle. Of course, we would like to generalize this to actual and large-event integrators, right? So actual large-event thermostats that you would use in your simulation. And that is what we're currently working on. And I show you how to do that in principle, right? So how you would derive this random number difference for an actual large-event integrator. What I show you is the ABOBA method. That's one of the splitting operators, splitting algorithms that you might know from works of Ben Leimkuhler, Gary Brooks, or John Codera. And they now have 6 steps, A, B, O, B, and A. And the way to derive delta eta k for this one, right? So there's one random number drawn somewhere in the middle, and you ask the question, what random number should I draw in order to get the same step with a different potential, where the potential is evaluated at 2 positions. So that's a bit more complicated. And the way we do that is we write down the initial point, QK and PK, in this phase space diagram. So it's a phase space over here. So that's the initial point. And after one integration time step, we want to get to this final point over here, QK plus 1, PK plus 1. And the integrator breaks this transition down into 5 steps. A, an update in the positions, B, O, B, and 3 updates in the momenta, and then A again, an update in the positions. Now, these vertical lines, they don't depend on the potential whatsoever. So they will be the same whether you conduct this at V or at the target potential, at the simulation potential, the target potential. What changes are these B terms, because they depend on the potential over here and over here. But in order to get the same progress from K plus 1, we require that this distance remains the same. So if gray is your simulation, so the the simulation potential B1 O plus B2, then in the reweighted simulation B2 and B1 might have changed, and then O needs to compensate this change in distance such that you have the same distance over here. So these 3 terms need to be the same as these 3 terms in the reweighted system. Yeah? And the updates, the distances you get from these 3 equations in here, and then you change the potential and solve for delta eta k. And what you get out is something that looks like this. And this again looks very close to the Euler-Majorana expression, the overdamped expression. And we tried that for a few large-event integrators, and it seems to work really, really well. So here is the reweighting for the ABOBA scheme. Again, our triple well potential, and the eigenvectors are right on top of each other. So that's a direct simulation. That is the reweighting with ABOBA, where we use this equation. And that's the reweighting with the approximation, yeah, where we use the overdamped Langevin equation. And we also tried a stochastic position valet, and that also seems to work very well. So this approximation seems to hold up for many Langevin integrators. What this means is that maybe, probably, that is something that we're looking at right now, you don't have to derive this delta k for each integrator separately, but you can kind of import the Langevin integration expression, right? So then a general path probability for Langevin dynamics would look like this. You record your random number at the simulation potential, and that is easy. You can just write that out into a file. You also need to record the bias at each integration time step. And then you evaluate delta eta k using this expression. And that seems to be universal from what we see currently. And that would mean that path reweighting becomes actually technically very tractable using MD programs like OpenMM, where this is easy to implement. It would become something that is relatively simple to integrate, because the only thing that you need to evaluate is this equation. And with this I close, and I would like to thank my group for working through this pandemic. What I showed you today is work from Luca Donati, who started the path reweighting project, then in particular Stephanie Kieninger's work, who did the exact and approximate path probability ratios for Langevin dynamic. And then the last thing that I showed you right now is something that we're doing together with Simon Giesbrecht and Stephanie Kieninger. And we started a project together with Carsten Hartmann from BTU Cottbus. And funding, and you for your attention. I'm looking forward to questions.
Great, thank you very much, Bettina, for a wonderful talk. So we already have a couple of questions in the chat, and so a question from Peter Ballhaus. How does the path reweighting scale with path length? As the path becomes longer, do we not have exponentially more unlikely reweighting factors? And how does this translate into the rates?
Yeah. Sorry, I kicked out the frequently asked question slide. So yes, indeed, it scales. So the path probability goes down exponentially with path length. So if you pick a path length that is as long as the transition across a barrier, it's probably not going to work. So what we do is so if you think of these transitions, these going from I to J, these are really Markov model. So that the length of these paths is the length of the lag time in the Markov model. So orders of magnitude smaller than the slowest time scale in the system. So the combination of Markov models and path reweighting seems to work.
Great, thank you. So we have another question. Can you provide more details on our reweighting 3 one-dimensional method dynamics bias using the beta hairpin system? That's from Angie Babu Kapakalia.
What was the last one?
Can you provide more details on how you applied the 3 one-dimensional method dynamics biases for the beta hairpin system?
So what we constructed 3 one-dimensional biases, meta dynamics biases using Plume. So that's not we didn't sample the whole cube, right? Not the 3-dimensional system, but we had like 3 one-dimensional biases. And then to reweight this, what you need to have is the gradient of the bias with respect to, so where do I show you this? Here. So what goes in here is the gradient of the bias, but the bias now only depends on these 3 distances, right? So you only need the derivatives with respect to these distances. So if the bias is low dimensional, then also this gradient is going to be relatively low dimensional. So in R, it's it's 3 one-dimensional gradients, and then you need to translate this into Cartesian coordinates. Does that?
Great, thank you. So I had a question, but it may have been on your FAQ slide, which was the degree to which you can apply a bias. I think that you recommend not applying.
We don't know that actually. So sorry, we don't know that. How strong should the bias be? It's very difficult to analyze, right? So you can test that, of course, for many different systems, right? But to have a general recommendation is very hard to say, right? So what we find is the uncertainties become too large if you use the entire, like the fully converged metadynamic surface. What we do instead is we take the fully converged metadynamics surface and multiply or divide by 10. Yeah, so we take 10% of the full system, and that worked well for the systems that we looked at. But so what I maybe would also show. So when should you use it is maybe the more relevant question, or the one that I can answer at least, right? Is so what we did here is we have butane at 3 different temperatures, 300, 200, and 150. And so if so in all cases, we recover the correct eigenvectors by reweighting. By biasing and reweighting. At 300 Kelvin, this doesn't really give you a gain, especially at larger implied time, larger path lengths, then the uncertainties become large. So essentially, if you have a system where you can sample the Boltzmann distribution without bias, right? Even if you can wait long enough to get the Boltzmann distribution sampled, then you should use this. You should use direct sampling. But if you go to temperatures or barriers that you cannot cross with direct simulations, so here the direct simulation yields errors in the Boltzmann distribution and then large errors in the second and third eigenvectors, their reweighting actually gives you an advantage. Gets the eigenvectors, gets you the correct eigenvectors, and gets you at least sort of good estimates for the implied timescales. The slowest implied timescale is not so. Sorry, that is actually, we think that is a wrong estimate, to be honest. So that's the direct estimate, but the direct estimate didn't converge the Boltzmann distribution, so that is probably a wrong estimate. So this is a method to be used when you cannot sample directly. I think then this is
great. Thank you. And then we have maybe time for one final question from the chat from Anmol Kumar, who asks, how does the time step of the simulation influence the path probability?
Good question. Yes. So you're a bit limited with the time step because you still have I mean, you would need to constrain so you're limited to 2 femtoseconds because of the potential energy function. That no reweighting method is going to change this, right? So if you don't constrain bond length and angles, you cannot increase your time step. But suppose you could increase your time step, right? Then let's see whether I have a good here. So here we plot the error as a function of xi delta t. Xi is the friction, yeah, or sometimes this is called, in Gromics, this is called the time scale of the integrator. And it's often set to something like 1 over picoseconds. So an order of magnitude larger than the implied time scale, than the time step. So if you set the time step to 2 femtoseconds, you're running your simulation in this regime. If you increase the time step and keep the friction the same, then eventually you will get into a regime where this is not accurate anymore, right? So where where both the integrator and the reweighting is not accurate anymore. But this sets in really at 100 femtosecond time scale. So it's for a long range, these are actually. So we're not, yeah, so at least until 10 femtoseconds, I think the larger one integrators are stable, and the reweighting is stable until 100 femtoseconds, yeah. Supposing that you could simulate at 100 femtoseconds. So there's a huge margin until you run into any accuracy errors with the time step, because so far we're limited to 2 femtoseconds, or maybe 4.
Great, thank you very much. And so, so please join me in thanking Bettina again for a wonderful talk, and thank you to all the presenters.